Okay, we're going to discuss VSEPR theory now as a way of predicting the geometry of a molecule. So VSEPR theory stands for valence shell electron pair repulsion theory. The first thing we have to do when looking at the geometry of a molecule is to identify how many electron groups are around the central atom, or a central atom. VSEPR theory will focus on predicting the geometry, or the three-dimensional shape, of a central atom. And so we're going to start with three examples of simple molecules: methane, ammonia, and water. First thing to ask ourselves is, how many bonds do we see around the central atom? And you can count just sigma bonds, or you can count double bonds equal to single bonds. It's really just the number of bonds. And so, in this case, around methane we have 4 bonds. Around ammonia we have 3 bonds. And around water we have 2. We also need to count the number of lone pairs. So how many lone pairs are around the carbon in methane? 0. How many are around the nitrogen in ammonia? We see 1 lone pair. And around the oxygen in water, we see 2 lone pairs. And so we add these up. In these cases, conveniently enough, they all equal 4. And we're going to call that the number of electron groups. Now this can come from, again, bonds and lone pairs. We add them up and we get 4. And this tells us there's 4 electron groups around each central atom. And what VSEPR theory says is that these electron groups will arrange themselves so that they are as far apart as possible from one another. And so we might think that here methane, they arrange themselves in 90 degrees from each other. But in reality, they adopt what's called the tetrahedral geometry. So let's look at methane first, and then we'll look at the rest of these molecules. Methane has a carbon, and I'm going to draw this not as the planar representation we saw at first, but in an attempt to indicate the three-dimensional relationship between these 4 hydrogens that are surrounding the central carbon. And I'm going to use this thick wedge shape to indicate that the molecule is, or I'm sorry, the atom is projecting out of the page. And that should be an H right here. And then I'm going to use a dashed wedge to indicate that it is projecting back into the page. So these 2 hydrogens are in the plane of the page. And these 2, one's coming forward, one's going backwards, and this is called tetrahedral geometry. And so that is what the shape of the methane molecule is. And in fact, the bond angle, the HCH angle equals 109.5 degrees. That's the bond angle between H, C, and H. So you can see that it is greater than 90 over here, as indicated by our flat planar drawing. So this is electronic tetrahedral geometry. Restate that. The electronic geometry is tetrahedral. Equals tetrahedral geometry. And in this case, no lone pairs, the molecular geometry or shape equals also tetrahedral. So we see with the number of electron groups equals 4 and 0 lone pairs, we get tetrahedral molecular geometry and electronic geometry. Tetrahedral, I'll abbreviate it, and I'm sorry, let me put electronic geometry first. So electronic geometry equals tetrahedral, and that's for all of these, so we'll make that stretch for methane, ammonia, and water. And the molecular geometry, in this case, equals tetrahedral.